I hope you had a great Christmas, and it's time for me to go through the solution of this sum of n-dimensional integrals. Okay, let's do it. So the first thing I'm going to do is I'm going to call the n-dimensional integral I sub n so we can work with it easier. And I'm going to call the big sum, I'm going to call it S. And let's shift our focus to I sub n. We're going to try to evaluate this on its own first. And so I'm just going to copy down the expression up there. And we can notice that if we can get rid of the denominator, then it will just be a product of the logs of the individual dummy variables, which means the integral can be separated into a product of integrals. And so this really calls for differentiation under the integral sign. What I'm going to do is I'm going to insert a parameter called alpha, and I'm going to insert it right there. As you can see, I've inserted it as the exponent of the product of dummy variables. And now, if I take the derivative with respect to alpha, I'll get something like this. I'll have an extra log of the product of dummy variables, and now I can just cancel them out. And so that leaves me with just this. I can get rid of the denominator. And what did I say that meant? That means that we can separate this into a product of integrals. And not just a product of integrals, but like the product of the same integral, which means we'll end up with the integral of x to the power of alpha log x dx to the power of capital N. And I'm just going to turn these into round brackets just because I like that more. But what we can do now is that, that's from 0 to 1. And we can use integration by parts. And that's going to give me, this is the UV part, 1 over alpha plus 1. I'm going to write that a bit better. 1 over alpha plus 1 times x to the power of alpha plus 1 log x from 0 to 1. And I'm going to take away integral of v du, which is integral from 0 to 1 of x to the alpha over alpha plus 1 dx. And that's to the power of n. And let's take a look at this front term. So when we plug in 1, it's obvious that it's going to be 0. If we plug in 0, it's also going to be 0, and you can check that by L'Hopital's. So I'm just going to skip that, and I'm just going to say we're going to have negative 1 over alpha plus 1 times this integral right here to the power of n. And this integral is fairly trivial, so I'm just going to compute that, and this will give us this expression right here, negative 1 to the power of n, divided by alpha plus 1 to the power of 2n. And remember, this was I sub n prime of alpha. And so to get I sub n of alpha, we can just integrate I sub n prime of alpha with respect to alpha. And so I'm just going to plug that in. And I'm also just going to integrate this. It's pretty straightforward to integrate. There we go. That was literally just the power rule. And so what we have to do now is we have to find c. And to find c, let's take a look at our original expression for I sub n of alpha. We have this. And we notice that all the x's are between 0 and 1. So if we set alpha to infinity, then it collapses to 0. And so what we're going to do is we're going to take the limit on both sides to infinity. We're going to have the limit as alpha goes to infinity. And the left side is going to be equal to 0. The right side, let's see. The right side, we're going to have alpha blow up to infinity, but 1 minus 2n is a negative number, so that's fine, because n will always be greater than or equal to 1 as an integer as well. So that's going to be 0 as well. And what we're left with is c equals 0. And so I sub n of alpha is actually just negative 1 to the power of n plus 1 divided by 2n minus 1 times alpha plus 1 to the power of 1 minus 2n. And taking a look at our original I sub n is just I sub n of 0, where alpha is 0. So we are looking for I sub n, which is equal to I sub n of 0 And plugging that in will give me negative 1 to the power of n plus 1 divided by 2n minus 1. And so now that we have an expression for I sub n, we can take a look at our sum, which is s equals the sum from n equals 1 to infinity of I sub n. So let's write that down, and I'm going to plug I sub n in. And let's take a look at this. So this, if we write it out in its expanded form, it's going to be 1 minus a third plus a fifth minus a seventh, on and on and on. And it's just the alternating sum of the reciprocal of the odd numbers. And if you don't even have to do a lot of calculus to do this, well, to know this. That's just the Leibniz formula for pi. And so this is exactly equal to pi over 4. And that is our value for s. And this even generalizes. So this generalizes to, if we say s of alpha, let's say s of alpha is the same sum, but we define it as the sum of I sub n of alpha, then we find that this is equal to the inverse tangent of 1 over alpha plus 1. Isn't that just cool? So pi over 4, that's our final answer. I'm going to put a box around it. See you in the next one.